Hi sir, this is Emily, so I'm going to do this observation video now. So first of all, we're going to look at the question 1a. So the question gave us the concentration of the initial N2 and O2, and also the concentration of N2 at equilibrium. So we can just set up a ice table, and we know that the initial concentration of the product is, in this case, is 0. So we can just set S table and let the change here to be X, because according to the coefficient, it's 1, 2, and 1. So because it has no products at this time, so we have to go forward to make products, and in which the change of the reactant will be negative. So according to the coefficient, it will be negative X, negative 2X, and also the products here will be plus X. So we can use the concentration of N2 initially and at equilibrium to calculate what X is. So it's 0.4 mole per liter. So we can just use this number to substitute into these other X's to calculate the concentration for O2 and N2O4 at equilibrium. So after we got those concentrations, we're going to put them into our KEQ equation in order to find our KEQ. So the KEQ is basically the concentrations of products over the concentrations of reactants. So for our products, only one of it is N2O4. But for the reactants, there are two. One is N2 and the other one is O2. And we also need to know that the O2 has 2 moles, in which in this case we have to square the concentration of the O2. And we can just put those numbers into this equation, and we get our final number of the KEQ is 0.8. So I can also mention that because 0.8 is smaller than 1, so which means that reaction we're going to favor reactant. Okay, so for the next question is 1b. So it asks us what will happen if we increase the pressure of this reaction to the so what actually will happen to the concentration of O2. So basically, according to Le Chatelier's rule, if we increase the pressure of the reaction wanted to decrease the pressure of the system. So we can see from the right side here, we only have 1 mole of gas. But for the left side, for the reactant here, we have 3 mole of gas, which means that the reaction is going to shift forward in order to produce less mole of gas for the lower pressure, because we increase the pressure, so it wants to lower the pressure. So it goes where it has less mole of gas to produce N2O4. So which means that the concentration of O2 will decrease, and same as N2, because it has to consume the reactants to make the products. So that's why the concentration of O2 will decrease. So next question is asked about what will happen to the concentration of N2O4 if we increase the temperature of the reaction. So basically, you can see from the question is that the forward reaction is actually a exothermic reaction. So we can just write heat as a product for the forward reaction. And so if, according to Le Chatelier's principle, if we increase the temperature of the reaction, the reaction wanted to decrease the temperature. So in which it will shift backwards in order to do a endothermic reaction to absorb heat from the surrounding in order to decrease the temperature. So as a result, the concentration of N2O4 is going to decrease in order to make more reversed products in this case. So next question is 2A. So basically, 2A gives us the KSP of AgCl, and it wants us to find out the solubility of AgCl. So we can just write the dissociation equation first, and we set up an S table, and we don't care about solid in equilibrium. And also we know that the products initially will be 0 in this case. And also the coefficient in front of it are 1 and 1. So which means that their changes are going to be plus x. Because there are no products initially, the reaction has to go forward in order to make products. And also the concentration at equilibrium will also be x and x. So we can use the formula of KSP, which is the concentration of Ag times the concentration of Cl minus. We don't care about solids, so we don't involve it in our KSP equation. Just consider it as a constant value. So we put our the x into it, and also the number of it, the KSP. So we calculate the x is equals to this number, and this number will going to represent the molar solubility of AgCl, which means that the amount of salt AgCl that dissolved. So that's how it means by this x. So the next question will be the 2C. So I want us to define, after these two solutions mixed together, were there any precipitate were formed? So basically we can just write this double displacement reaction first of all. So we get two products in this way, and we only know the KSP of AgCl, and we can see it's really small. So it may favor reactant, so we just assume that the AgCl will form precipitate. So we write this expression of the dissociation reaction for AgCl, and in order to know if it's going to form precipitate or not, we have to find out the QSP to compare with KSP. So the QSP, we have to note the concentration of Ag plus and also the concentration of Cl minus. So we have now to figure out these two. So how to find out the concentration of Ag plus is, we can look back to our equation here. We can find out here the Ag is actually, the concentration of Ag is the same as the concentration of AgNO3, because the ratio is 1:1, which means that 1 mole of AgNO3 will have 1 mole of Ag plus. So they're the same. So the most important thing here is that the two solution mixed together is going to dilute, it's doing dilution for both solution. So in which means that we have to use the dilution equation, which is C1V1 equals to C2V2. So we use this convert equation and put all the numbers into it, which is the original concentration before diluted, and also the original value before diluted. So here is the value after the dilution happened, which is just simply add the two values together. So we get our diluted and the concentration of Ag plus we wanted. And then we have to find out the concentration of Cl minus. So also go back to this equation. You can see that the MgCl2 here, and also the Cl and MgCl2 ratio is actually not 1:1, is 1:2. So in which means that there in 1 mole of MgCl2, it will have 2 moles of Cl minus. So we have to times 2 for the MgCl2 in order to let the concentration equals to the Cl minus. So after we substitute the numbers into it, we get 2.50 times 10 to the power of -4 mole per liter for our concentration of Cl minus before diluted. And also we have to use the dilution equation to put the initial concentration, to put the initial volume and diluted volume into it, and we get our concentration of Cl minus after diluted is 2.499 times 10 to the power of -4 mole per liter. So we just simply put those concentrations here into our equation to calculate the QSP. So which is 1.374 times 10 to the power of -8. And also our KSP for AgCl is 1.77 times 10 to the power of -10. So it's obvious that the QSP is bigger than the KSP. So which means that it is supersaturated and means that there are too much products. So the reaction wants to go reversed to form the solid, which is AgCl. So we get the conclusion is that this reaction is going to form precipitate, which is AgCl as precipitate for this reaction. So the next question is 2b. So basically why the solubility of AgCl is lower in the solution of NaCl. So it's basically caused by the common ion effect. So when AgCl dissociates to make Ag ion and Cl ion, but before the solution NaCl is already have certain amount of Cl ion. So like when it turns to dissociate the AgCl, it means that it already has certain amount of chloride ion in the solution, which is like here we can see an example. The initial concentration of Cl ion will be like maybe assume that 2 mole per liter, so it's quite high. So as a result, it won't need too much of Ag ion or Cl ion to achieve the KSP. So basically we can see this equation here. So we already have Cl ion initially, so we only need a little bit Ag and Cl ion to achieve the KSP. So the reaction was still going to do forward to make a little bit Ag ion and Cl ion because the Ag initially has nothing, so it has to produce those products, but will not produce too much. So that's why the AgCl will not really have a high solubility in NaCl than in the pure water. So we can give an example, like for this ice table, we can assume that the initial concentration of Cl ion is 2 mole per liter because of the NaCl solution, and Ag ion is still 0 mole per liter because Ag ion is now included in that solution. And then we do all the steps and we get our x and 2 plus x. We put all of them into our KSP formula. So we get our x equals to 4.43 times 10 to the power of -11. So we can compare this to the solubility of AgCl in the pure water, so which are quite a huge difference. So it is much lower than in the pure water. And so those are all caused by the common ion effect. Yeah, and thank you, sir, for listening.